Good morning. My name is Tom Isenhart, and I'm a professor in the Department of Natural Resource Ecology and Management at Iowa State University. And we're here on a gorgeous Wednesday morning in June in the Bear Creek watershed, where we're going to be talking about saturated buffers. We're at the site of the first saturated buffer that was established in 2010. But before we went down and took a look at that, I thought we'd take the opportunity to give a little bit of history of where the idea of a saturated buffer came from. And a little bit about the Bear Creek watershed. So we started up here working in the Bear Creek watershed on private lands 25 years ago when my close colleague Dick Schultz was engaging with a landowner just downstream from here. And at that time he was interested he was cropping right up to the edge and had pasture right up to the edge, and he was interested in establishing some conservation buffers along his stream. Funny to think now that we look at a filter strip or riparian forest buffer in the Iowa landscape, and they seem kind of common. Well, back in 1990 there were very few of them, and there were very few cost shares or incentive programs for landowners to establish those sorts of conservation buffers. Again, we started in 1990 down on the Ron Risdahl farm, and with a 3-zone model that had trees nearest the stream, and then shrubs, and then native grasses and forbs at the interface between the crop field and the buffer. The projects expanded rapidly after that, and then in 1996, when the CRP program was amended to provide incentives for these sorts of conservation buffers, then things really took off, not only in Bear Creek watershed, but statewide. Since 1990, we've now expanded to working with over a dozen private landowners within the watershed, and we have over 10 miles of conservation buffers that we established, and our landowners have certainly established many more within the watershed. And so you can see the picture, or you can see the landscape behind me is an example of a riparian forest buffer that has several zones of trees and then grasses nearest the crop field. So what we've done during that time is that our role at Iowa State University is to really dig into some of the science about how these buffers work, and then feed that science back into some of the programs to improve them. And so we've had now over 30 graduate students that have completed their degrees up here at from Iowa State University that were looking at all the real details of how the buffers work, above and below ground processes. And we saw that there's a lot of change from wildlife habitat, increase in wildlife habitat, birds, fisheries improvement and changes, increase in below ground biomass, carbon sequestration within the streams, a reduction in greenhouse gases, an improvement in those bacterial processes that process that nitrogen. So the bottom line is we found that buffers work for a lot of really, really great things. But the one challenge we had is that like many landscapes within the north central region of the state of Iowa, all the land that we see around us, in order to make it profitable for farming, has artificial subsurface drainage or tile drainage. So it has a network of those subsurface or those underground plastic tiles that drain this flat landscape up here, and then takes it down through the waterway, and then in a pipe that goes right through the riparian buffer that we see below us. Well, so what that does is that essentially short circuits that buffer for any pollutant that is contained within that tile drainage. And of course the big one is nitrogen that moves with that tile drainage. So the challenge we had is that we had a large number of these tiles within these landscapes that would move right through these riparian buffers, again short-circuiting those buffers for any water quality improvement. So we were considering alternatives for how to address the issue of tile drainage moving right through the buffers, and there were several new conservation practices that were coming online. One was the nutrient removal wetland that are supported through Iowa Conservation Reserve Enhancement Program, but those nutrient removal wetlands are really for a larger watershed. They're more of a small watershed practice and didn't really work well for those small tile drainages that came through these buffers. The other one that was coming on the scene was our bioreactors, and they are a viable option and remain a great option to address this issue. Giving credit to one of my close colleagues, Dan Janes from the USDA Agricultural Research Service, recently retired, he came up with this brilliant idea that said, hey, why don't we intercept that tile drainage and then reroute it through that buffer, thereby getting all the benefits that are already existing for the buffer, and get a added benefit that is for nitrate reduction. So what I'd like to do is, the first saturated buffer was established right below us. Why don't we go down and take a look? We discussed the issue of how the tile drainage would short circuit this nice riparian buffer that we have here, and that we came up with the idea of a saturated buffer. So here we are at the very first one. So a quick description of what they look like. So the tile drainage drains about 25 acres initially behind us, drives down through this waterway, goes right where I'm standing here, and then outlets into the stream directly behind me. So what we did with the saturated buffer is that we have this control box, and the control box intercepts that tile drainage. So dig the tile drain up, put this box in line with that tile drainage, and this one has 3 chambers, and in the middle chamber in this one, if you can imagine below my feet, there are distribution lines, which are just perforated drainage tile, and that drainage line then goes out from this control box, sort of up towards the edge of the buffer, and then extends 900 feet upstream and about 100 feet downstream. Well, that's a perforated drainage tile. So then what we do is we have these gates in here, and we can raise and lower these gates, and we can set that water level. So what we'll do is we will set that water level so that it's about comes up to about 1 foot below our ground surface. The tile line is about 3 feet down, but we put those gates in so that water level comes up to about 1 foot below the ground surface. And with that head on it, what it does is that it takes a portion of that tile drainage, as much as it can, and it redistributes that tile drainage water out into that perforated tile, where it then leaves that perforated tile, enters the riparian soil, the stream bank soil, and then slowly moves through that stream bank soil towards the stream behind us, and then that's where all those microbial processes will remove a lot of that nitrate. So several important design considerations is, one is that we don't want to remove any of the drainage right from the upstream drainage. And so the nice thing about this is that it just has the gate, and that any excess water that isn't being distributed out into those tiles just goes over that gate and exits back into the stream. So there's no removal of any of the drainage capacity upstream. Several of the other design considerations we like is that one of the things we like to see is that if we have a little bit of slope right next here to the stream. And the reason we like that is that when we put those control structures in there, we're going to raise that water level to 1 foot below the ground right here. And if you take that back towards the field, we like to make sure that raised water level, the footprint of that raised water level, stays within the buffer. So that is, we're not moving any of that water back into the field. We're not backing up any of that water into the field. So water quality improvements have been impressive. To be honest with you, it's worked way better than we ever thought. In this site, we see that of the water that gets into the riparian soil, virtually all 90+% of that nitrate is removed before it hits the stream. The total amount of nitrate that is removed from this tile that's draining the land in front of me is limited by how much water we can get into that drainage line. So all of that water that we can get into that distribution line, we're going to remove that nitrate, but then how much can we get into that drainage line? That differs by how much the flow of the tile, how episodic that tile is, the type of tile drainage that's in the field. But in this case, on an annual basis over the last 10 years, we've been redistributing about 40% of that nitrate, of that tile water, has been moved down that distribution line. So in total, over that 10 years, we've been removing about 40% of that nitrate that would have entered that stream has been processed by this riparian buffer. So I suggest, rather than just relying on what I'm saying about the history of our water quality results, let's take a look. So what Billy Beck has in his hand right there is a nitrate test strip, and so he's going to just take that test strip and put it down into the control structure and dip it into that water, and then we're going to wait a minute and we'll see what the concentration of nitrate is, and then we will move down to one of the wells and see what it looks like after it moves through the soil. Okay, so how do we measure then? We will get the concentration of nitrate that we see in the control box, which is the tile drainage concentration. But how do we measure the effectiveness of the buffer? Well, in a number of locations, upstream and downstream, we have a transect a series of wells that go between where the distribution line is and the stream. And so this is an example of just a 2-inch PVC well. We took the cap off. One of the things we see here is a long line, and then that's a pressure transducer, and we use that to measure the depth to the water, and so we can see that water table fluctuation. And then for water quality sampling, we just have a plastic tube with a perforated bailer on the end, and we place that down into the well, and then you just start bailing on it, and the pressure will bring the water up, and Billy has a test strip that's ready to go, and he's going to dip that into that. And then we will wait a minute and we'll compare it to what we saw within the control structure. Okay, so then we have the two test strips, the one that came from the control box and the one that came from this well. And so the way you estimate the concentration of nitrate is that you just have this color scale on the side of the tube, and then you just move that up and down and compare it. And so, Billy, where are we? That's 11, 23. You want to estimate so in between there? It's somewhere in between.
Say 20.
So maybe about 20 parts per million nitrate as nitrogen. And so then this is the one that we got from the well, and we're probably about, what, 25 feet from the distribution line. And if we estimate that we're, what would you say there?
Under 5.
Under 5 milligrams per liter. So we've already reduced it by a significant amount just in 25 feet.